Today we'll look at how to analyze a gasket with Nastran solution 402 to see if it will leak. There are a number of considerations unique to analyzing a gasket. First is the definition of the gasket material. We first need to select an isotropic gasket membrane material. Next we'll need to specify the other properties, such as the yield pressure, which, if exceeded, will cause the gasket to plastically deform and not return to its original shape after the load has been removed. Depending on how far the gasket has been plastically deformed, we can define several unloading curves that define the shape the gasket will take once the load has been removed. Only one unloading curve must be specified. The last unloading curve must use the rupture point on the loading curve, which is the last point. The gasket finite element model must consist of only one layer of brick elements. When editing the mesh collector to define the physical properties for the gasket, we need to specify both the gasket strain material and the material coordinate system. This coordinate system must have its x direction defined in the direction the gasket will be compressed. When defining contact, it's important that the source region be on the softer material, which is the gasket side. While not mandatory, if there are any initial gaps or penetrations in the geometry, we can remove them by specifying multi-step nonlinear kinematic contact pair parameters to set gaps and penetrations to an interference of gap val and setting gap val to 0. The fluid penetration pressure will help us determine at what pressure the gasket will leak. A unique fluid penetration pressure must be specified on each contact region. So for this model, we'll be defining 4 fluid penetration pressure loads. The fluid pressure must be defined by a time-dependent field that will increase the pressure as the simulation progresses. The fluid penetration pressure will leak from the fluid path starting points into areas where the contact pressure is less than the contact pressure tolerance, only if it can find a path to it starting from the fluid path starting points. Here I've set the contact pressure tolerance to 1 psi. If the contact pressure is less than 1 psi, the fluid penetration pressure will be applied to the leaked region. When running a gasket analysis in solution 402, the stress-strain curve defined in the material property will be used. However, the type of stress and strain can be defined by whether or not the large strains checkbox is selected. Selecting the checkbox will use true stress strain. If it's not selected, engineering stress strain will be used. When using contact with solution 402, it's important to set a global nonlinear control parameter for matrix symmetry to unsymmetry activated. The solution will not be able to converge without it. We'll begin by opening a model of a boss with a gasket and a cover and some bolts. We'll create our simulation files in the Simcenter Nastran structural environment, and we'll create a new solution 402 multi-step nonlinear kinematics. I will call it 402, and we'll select some options. First is for material nonlinearity. Next we'll go to case control, where we'll specify our global nonlinear control parameters to turn on the unsymmetric matrix symmetry. And also we'll select some output requests that are specific to running a gasket analysis. So here we can turn on our contact results as well, since we'll be using contact, but we want to make sure we definitely get our gasket results turned on as well as our pressure results so we can see our fluid penetration pressure results. Alright, the first subcase we'll create is going to be a preload subcase for our bolt preload, which we'll be setting up a little bit later. We'll select 5 increments. We also want another subcase. Let's go back. First we'll edit our preload subcase. We don't need any nonlinear control parameters, so I'll set that to none. And we'll create a new subcase. This will be a nonlinear static subcase, which is where we'll be applying our internal pressure and our fluid penetrating pressure. And here we don't need any additional nonlinear control parameters. We'll let it run for 1 second and 20 increments. Alright, next we'll go to our idealized part where we'll prepare our geometry for meshing. So we'll begin by getting our associative copy of the geometry, and next we'll go ahead and trim the cover, the gasket, and the boss for symmetry. And to do this we'll define a midplane. Alright, that looks good. Now we have the original geometry on different layers so that we can leverage that for making it easier to work on the part and controlling the visibility. So here I'll turn off the layers, all except for those that have the bolts on it. And I'll go ahead and prepare the bolts for brick meshing by splitting them by the top of the shank. Now we need one more split in here as well, which will help us for applying our bolt preload. And for this we'll split the shanks by a midplane on the cover. So here we'll turn on the cover and we'll use that to generate a midplane. And that's where we'll be applying our bolt preload. Alright, next we need to divide the face of the cover by the face of the gasket. And this is important for specifying our fluid penetrating pressure, which we'll be doing a little bit later. Alright, that looks good. Next we'll prepare the boss for brick meshing. First we'll create a ruled surface that will help us divide the boss into brick meshable pieces. And we'll use the tangent curves there for selecting our section curves. It's a lot easier than picking them individually, which we could do as well. But if we select the tangent curves, we can get all of them in one shot with one click. Alright, next we need to generate a swept face for our next split. And to do that, we'll first offset a curve in that face. And also I think it's important to make sure that that curve is trimmed to the extents of the face. So we'll turn that on in case it's hanging over or it's not long enough. It can be extended or trimmed automatically as part of that offset in face feature. And then we can use that curve to sweep along the tangent edges of the top of the boss. And we'll use that face to divide the boss as well. And that is all we'll need in order to be able to brick mesh the boss. So let's go ahead and split it. And we'll split it by those two sheet bodies that we just created. and for some reason it places those resulting split bodies on layer 11. Let's go ahead and move those back to 13. Alright, so that looks good. Let's go ahead and turn everything on and go to the FEM. And here I had selected all bodies to use when I created the FEM. I don't need those other two bolts. So let's go ahead and edit the bodies to use. Let's turn everything off, and then we'll edit the bodies to use again. And instead of selecting all bodies, we'll select just those bodies that we want to use for meshing. Alright, that looks good. Alright, so we'll begin by meshing the boss. Let's go ahead and turn off everything except for the boss. To ensure we get a congruent mesh across these three bodies, let's create a glue coincident mesh mating condition. Here you can see it's created two of them across the three bodies. Now, before we can brick mesh one of these bodies, we can see we've got some partitions in the face that we need to remove. So we'll use the merge face command to do that. Now this merge face command, while very handy and enabling us to create a brick mesh on this body, if we were to process a CAD change to this body, we would need to merge these faces again in order for the brick mesh to update. This merge face command does not survive a CAD change or a finite element update. So now we're ready to mesh. We'll go ahead and use the multi-body automatic method with an element size of 1/10 of an inch. And that looks good. We've got two elements through the thickness there. So now we'll set some physical properties for the boss. We'll give it a name, and we'll select a material out of the library. Alright, next we'll mesh the gasket. Same element size, we'll put it into a new collector. And here we have a gasket material that I've created and put into a custom library. So we'll select that gasket strain material. And we also need to define a material coordinate system, and we need to have the X in the direction of the gasket compression. So let's get back to that once we first create our coordinate system in the correct orientation. So first we'll put our work coordinate system as the CSIS of an object, and we'll select the edge of the hole. That will orient the z-axis along the axis of the hole, but we want the x-axis to be along the axis of the hole or in the direction of compression. So we'll go ahead and drag one of those handles to dynamically orient the coordinate system, and then we can use that work coordinate system in specifying our material coordinate system as being offset from the work coordinate system. So here I'll select offset CSIS, and our reference will be the WCS, our work coordinate system. Alright, let's take a closer look at the gasket material. So the gasket material references a gasket membrane material, which is just an isotropic material with a mass density, Young's modulus, and Poisson's ratio. But the gasket strain material is special in that it references that membrane material and then specifies a number of other properties, including the loading and unloading curves. And here we'll go ahead and plot those so we can see how they're created. So that's our gasket loading curve. Then we'll go ahead and overlay the unloading curves as well. And we only need to have one unloading curve, and that needs to finish at the rupture point, which is all the way at the end of our gasket loading curve. Alright, so next we'll go ahead and brick mesh the cover. We'll use the until target method so that we can select multiple source faces going to a single target. Use the same element size and we'll put it into a new collector. And we'll name this one our cover and assign a material out of the library. Alright, and lastly we have the bolts. So since we have multiple bodies for our bolts, let's go ahead and create glue coincident mesh mating conditions so that we'll get a congruent mesh across all of them. And then we'll go ahead and create our brick mesh. And I'm going to just brick mesh the head first so that we get a nice looking mesh there. And then I'll go ahead and mesh the rest of it. And we'll put it all into the same collector. Alright, that looks good. We'll go ahead and name that collector and assign a material. So now we're ready to go to the sim, where we'll assign some constraints and loads. And we'll put those constraints on layer 1. And I don't want them going into my active subcase, so I'll deactivate it just by double clicking on it there. And we'll begin by creating a symmetric constraint on our symmetry faces. Next we'll create some fixed translation constraints. And now we'll begin to define our contact by first defining some surface regions. So here I'll use the body focus to make it easier for me to select the faces that I want. I could use the query select as well, or quick pick. This is just another method to simplify the selection of faces when you've got coplanar faces. Alright, so we'll call that bolt washer face. Next surface region will be our bolt shank. Here we'll use the body focus again for that. Then we'll create another region for the top of the cover. And next will be the bottom of the cover. And these are only going to be used for the contact. So here I'll just select the face on the bottom of the cover that's going to be in contact with the gasket. Then we'll select a gasket top face surface region. and gasket bottom. Next we'll move to the top of the boss. And here, because we split it up into a few different bodies, we'll have to do it in a few steps here. So here I want to select the body first, and then I can select the face. But now there's another body over here as well that we need to add to our surface region for the top of the boss. And then we'll do our boss holes. And we'll use those to glue the bolt shanks in just a moment. Alright, so that looks good. Let's go ahead and create our surface contact. Now we do have automatic pairing algorithms, which we're not going to be using today. I'd like more control over that by using the manual method. So here we'll first create our surface-to-surface contact between the bolt washer face and the cover top. We'll set a static coefficient of friction, min and max search distances, and also some multi-step nonlinear contact parameters. Here's where we'll set our initial penetrations to a gap value of 0, as well as any gaps also will be set to 0. And we'll call that any penny 3 gap val 0. Alright, that looks good for our first contact. Next one we'll create between the gasket top, and it's important to select the gasket as the source face for the contact because it's softer. That will assist with convergence of the nonlinear solution. Then we'll set the same contact set properties and contact pair parameters. Alright, then we'll go from the gasket bottom, again the gasket being the source, softer material, to the boss top with the same properties and parameters. Alright, next we'll set up our glue between the bolt shank and the boss holes. And we'll take the defaults for that. Alright, so here we can see all the face contact and glue in our solution. Next we'll set up some bolt preload. Let's go ahead and hide everything except for the bolts. And here I'll just box select those two planar faces for our bolt preload. And we want to select the type as being force on 3D elements cut plane. And we're going to use that cut plane that we defined earlier. Now here auto sometimes works great. I want to make sure that we've got the correct direction, so I'll create a local coordinate system and we'll say that our bolt preload is going to be along the z-axis, and we'll put 1,500 pounds on both of the bolts. Alright, then we'll go ahead and drag that into our preload subcase. It would have gone in there automatically if that subcase was active, but it was not, so we can put it in manually. Alright, next we'll create an internal pressure. This will be our working pressure on the boss, gasket, and cover. And we want to ramp this pressure up with time. Now we had the solution earlier set up to run for 1 second and 20 steps. So here at time 0 we'll have 0 pressure, And at time 1, which is our end time, we'll have our full load pressure of 500 psi. Now this particular gasket needs to seal to 350 psi. So I'm going to run it a little bit past that to see where it fails. Now we'll put in our fluid penetrating pressure. And we need to put in 4 of them. The first one is going to be on the cover, so we'll use the body focus to just select that edge on the cover. And we could define a new region, or we could reuse that region that we created earlier for our cover bottom. Our fluid pressure we're going to take directly from our working pressure that we just defined on the boss, gasket, and cover faces that are wetted. And we'll select a contact pressure tolerance of 1 psi and a topology method for our wet region definition. Alright, next we'll move on to the top of the gasket. We'll use the same field again. All the rest of the parameters will be identical except for the edge for our fluid path starting points and our potentially wetted surfaces. Next we'll move on to the gasket bottom. Same pressure field, contact pressure tolerance, and wet region definition, being topology based method. Alright, and then lastly we have our boss. Select the edge of the boss, boss top region, fluid pressure field, and our contact pressure tolerance. Alright, so that should be it. There we can see all of our loads, face contact. Let's go ahead and solve. And we'll go ahead and save as well. I'm going to go ahead and pause the movie while it's solving, but here we can see the contact convergence and iterations as well. And I'll go ahead and pause the movie. We can see it takes a total elapsed time of about 1.5 minutes. Alright, so let's look at our results. And the key result that we want, first you can see here that here's our preload steps if we wanted to see the bolt preload and what kind of contact pressure that's generating on our gasket, we could. Let's go ahead and start at the last step, which is when we have our full pressure of 500 psi applied. Now we can see in red that we've got leakage. Blue is where we do not have leakage. Also, we're looking at all 4 fluid penetration pressure results overlaid on top of each other. Let's go ahead and step back as we're decreasing the pressure to when we just get leakage. So this step looks like we're just before leakage. Let's go ahead and turn off some of the other meshes so we can see a little bit better exactly where it's leaking. So here is the boss, the gasket. You can see that's not leaking yet, and the cover. All of those independently are not leaking. Now if we go to the next step, what we'll see is we've got leakage. Now we have a path across the gasket for the fluid to penetrate. We can also see that the fluid is leaking at 275 psi, so we really only have 250 psi of pressure that we can seal. And we need 350 psi. So what do we have to do in order to get more pressure margin? What we'll do is we'll make the cover a little bit thicker. See if that helps. So here we'll go ahead and make the cover thicker by 50 thousandths of an inch. Alright, so that looks good. Let's go back to the FEM. You can see because our mesh is associated to our geometry, we have a mesh update pending. Let's go ahead and turn on all the meshes so we can see them. You can see the geometry is a little bit thicker there on the cover, and the bolts are a little bit longer as well. Let's go ahead and update the meshes there. Next, we'll go ahead and clone our solution so we can keep our original results. And we're ready to solve. So here I'll go ahead and pause the movie. You can see again another minute and a half and we've got our updated results. So let's take a look at our old results with our thin cover, and we'll plot below our old results our updated pressure penetration on the bottom with our thicker cover. So you can see both of them are predicting leakage at 500 psi. So we can see this a little bit better. Let's go ahead and turn off everything except for the gasket. And here we can now step through and lower the pressure and see what threshold value we're getting leakage on our updated design. So here it looks like we've got sealing at 375 psi. We needed 350, so we've got a little extra margin there as well. Simcenter 3D accelerates the process of gasket analysis.